Hi dear students. In this session we're going to discuss another important topic, that is CPGET 2019 question paper. In this the questions framed from D block elements and coordination components. And I'm trying to explain you the basic concepts of these questions. And these questions these concepts are generally included in many of the entrance examinations. I'm trying to explain you these topics, including the CPGET 2019 question paper questions. And don't forget, subscribe and like and share my channel for more videos, which is very useful for chemistry entrance examinations. Let us see what are the different questions in the CPGET 2019. See, in this video, I have already told you the coordination compounds and the D block elements, Q&A session, and a complete explanation with basic concepts, which is very useful for different entrance examinations for various categories. Let us see what are these different questions. Let us see, the first one is going to be the order of stability of the complexes of Fe plus 2, CO plus 2, Na2 plus, Cu2 plus for the given lab. And Telugu medium students also, you can read here this question. Already there, I'm not explaining in Telugu, simply you follow this one. See, the order of the stability of the complexes, in this case, what to do is, let us take the answer is the first, third option is the answer. Why the third option is answer? This is going to be the answer for that. Copper plus 2 complexes are stable, then the nickel 2 plus, and then the CO plus 2 and Fe plus 2. Then what are the reasons for this one? Let us see. With the increase in the size, the stability of the complexes decreases. In the same series, with increase in atomic number of ions with the same charge, ionic radius decreases. Therefore, smaller is the size, higher is the effective nuclear charge. And here, you know, this atomic number is 29, 28, 27, 26 with respect to these elements, copper, nickel, cobalt, and iron. See, the ionic radius in angstroms, this is not A0, this is 0.69, 0.72. Therefore, you see here, iron is 20, here with increasing atomic number from 26 to 29, the ionic radius decreases. Therefore, the copper 2 plus complexes are more stable than the nickel and so on. And this is the why the third option is right. See, this is going to be the stability of the complexes of different ions. Now let us see which of the following do not obey effective atomic number. See, here you are provided 4 complexes and you are asked which do not obey effective atomic number, that is EAN. First of all, let me give you the answer. The answer is 2. That means 1, 2, 3 do not follow EAN. Only the fourth option will obey EAN. Let us see what is EAN. Actually, EAN is nothing but effective atomic number. It can be calculated by a formula called atomic number minus the charge present on the, or oxidation state, you can say. Atomic number minus charge on the complex or oxidation state of the element in the complex, then 2 into number of ligands. Why it is 2? Because each ligand donate one lone pair of electron. That's why 2 into number of ligands. For example, if you take the chromium, hexaaminochromium 3 plus complex, in this, the ammonia is a neutral ligand. That's why chromium has +3 oxidation state. Instead of the charge, you can take oxidation state also here. 24 minus 3, because 6 ligands are there, 2 into 6, that is going to be the 12, the total is 33. That is, effective atomic number is nothing but the complexes in which the central atom or ion, if it contain nearest noble gas electron configuration, that is said to be the stability. Therefore, the nearest noble gas for 33 or for the chromium is the, that is going to be the krypton, that is whose atomic number is 36. Here it is not 36. Similarly, if you go for the second complex, here the nickel atomic number is 28 because it is a neutral ligand, oxidation state is 2, and therefore there are 6 ligands, 2 into 6 and 12, that is going to be the 38. It is also not nearest noble gas, that is 36. And if you go for the cobalt 2 plus complex, this is also, you can see cobalt atomic number 27. It is a neutral ligand, therefore oxidation state is equal to the charge on the complex. And there are 6 ligand, 2 into 6, 12, therefore it is 37. It is more than 36. But whereas if you go for the hexamen platinum 4 complex, and here in this case, the atomic number of the platinum is 78. It is also neutral ligand. That's why it is going to be the what? 2 into 6, 74 plus 2, that is 86. 86 is going to be the atomic number of the xenon. That is radon, not xenon. And here it is going to be the radon atomic number. Therefore, this follows the effective atomic number. That's why these 3 compounds do not obey effective atomic number, and only this one. They on this concept also in various examination, you are getting questions. Try to learn this effective atomic number. Now let us see this another important and there is a different question on the magnetic moment as well as the color complexes, both having the same concept. Okay, here also there is a question on this one. The pair in which both the molecules have the same magnetic moment. Let me tell you, the first is the answer, that is going to be the second one. Only these 2 complexes. See how many actually in this included totally. One is chromium, another is a cobalt, another iron, manganese, only 4. And different combinations are given for the same complexes. And you are asked which contains same magnetic moment. Actually, what is a magnetic moment? The magnetic moment or magnetic property is nothing but, mainly it is classified in the 2 categories. One is a paramagnetic, another is a diamagnetic. So other also there like ferromagnetic, but according to our discussion, and mainly we have to know what is paramagnetic and what is diamagnetic, which substances possess shows the paramagnetic and which shows the diamagnetic. This you see, paramagnetic means the substance which contain unpaired electrons. They show the paramagnetic property. If they contain no unpaired electrons, all are paired, that is diamagnetic. This simple technique you to remember for a magnetic property. If contain unpaired electron, paramagnetic. If no unpaired electron, diamagnetic. That's very simple to answer this type of question. You see, this is the number of electron, it's a magnetic moment. Then magnetic moment is expressed in terms of Bohr magnetons. Here this is going to be 1.73. This value also you can remember with a tricky way. How does it is? If it is 1, it is 1 plus. If it is 2, 2 plus. 3, 3 plus. 4, 4 plus. 5, 5 plus. Means no need of remembering the magnetic moment also. If it is 1, just you remember in between 1 to 2. If it is 2, 2.83, 3, 3.87, 4, 4.90, 5, 5.2. See here also 7, 8, 9. Only 1.7, 2.8, 3.8, 4, 4.99. This is in this tricky way you remember what is its magnetic moment also. Then paramagnetic property is directly proportional to the number of unpaired electrons. More is the number of unpaired electrons, more will be the paramagnetic property. See, let us calculate this paramagnetic property. See in this, how does it can be calculated? How many? First, let us discuss how many unpaired electrons are there. If they contain same unpaired electron, suppose the 2 complexes contain 2 unpaired electrons, they are having the same magnetic moment, Bohr magnet. That's why first you calculate how many unpaired electrons in each complex, because there are only 4 is given. See, it has 4. How does it is 4? Because you know this chromium atomic number is 24 because it is a neutral ligand, and 2 electrons are lost, 21, and you'll get 4s034. You remember, I will give you one more hint. This is the atomic number. In case of the 3D series, whatever the digit is here, 24, 23 or 26 like that, and the same value is in this D4, D. And the first 2 electrons, whatever they lost only from S. That's why whenever you go to write the electron configuration, 24 means D4, 25 means D5, 26 means D6. If it is plus 2, 4s0, 3d4, 4s0, 3d5 like that. And here the 4 can be filled in this way. 5 degenerate orbitals, 4 orbitals. Therefore, 4 unpaired electrons in this complex. Now let us see in this complex cobalt tetrachloride cobalt complex. Here, this is a negative ligand. Therefore, you see the cobalt, what is electron count? 4 is there. Therefore, -2 it is. But it is going to be See, this chromium has 4, there is a cobalt has 3 electrons because there is 27 minus 2, 7 electrons are there in d orbital like this. You can have the 7 electrons, they are filled like this. So that what happened here, there are only 3 unpaired electrons. Now let us go for the iron complex. It is having a d6 electron configuration because neutral ligon, and iron has +2 electron configuration. Then how many? 4 electrons are there. Here, this is the 4 electrons is like this actually. The 4 electrons are these 6 electrons. First, they are filled singly, then get paired takes place. Therefore, 1 paired and 4 unpaired electrons. Now, manganese complex, here manganese atomic number is 25 minus 2. Because it is 25 atomic number, 5 electrons are there in d orbital 5. See, among these 4, which complexes having the same number of electron? Only chromium and hydrogen complexes, 4 and 4. That's why these 2 complexes having what is called the same magnetic moment, because 4 has 4.90, 7, 8, 9, you remember. This is very, very easy to remember without calculating. This is what is the questions framed on the magnetic property. You have to decide, determine the answer like this. Now, the same concept here also. Which one of the following is not colored? This is also on the same. See, let me tell you, the first of all, the answer is 4. Only the 4 one has, you have to remember another important point is in the question you will get confused. What is it? You forget about the not. You must remember whether in the question is no, not, does not, is there or there. You have to find out. Otherwise, which of the following is colored, you read, then you just simply take this answer. Not like that, read question properly. Okay, the fourth option is do not have a color. Okay, then what is the reason for this also? Let us see. See, presence of unpaired electron gives a color. I told you already, presence of unpaired electron also gives a paramagnetic property. Absence of unpaired electron gives no color. Absence of unpaired electrons gives diamagnetic property, because these are 2 are related. Paramagnetic colored, diamagnetic or colorless. That point you should remember. So that in titanium complex here you see titanium is 22 minus 2 because it here a +2 oxidation state. I already told you whatever the electrons present on our 20 plus, the 2 electrons will be always there in d orbital. This is 2 having the unpaired electron, that's why it is colored. Let us see the cobalt complex, 27 minus 2, 27, 7 is there in d orbital. I told you that 20 plus electrons always on the d orbital. The 7 electrons are filled like this, 5 first filled, the 2 are get paired up. Therefore, here 3 unpaired electrons, that's why it is colored. If you take the copper complex, here it is +2 electron configuration. 9 electrons are there in the d orbital. Therefore, here that 9 will be filled in this one. 1 will be unpaired electron, that's why it is also colored 1. And the last one, that is scandium complex, 21 minus 3, because there is a 3 electrons are lost, 2 from the s orbital and there is the remaining electron from the d, that's why it is no electron. There is no unpaired electron, that's why this is going to be our answer, which does not having any what is called any electron or unpaired electron, that's why it is colorless. Okay, we find out the answer like this. Now, this is another important concept that is generally is giving in a different entrance examination. The crystal field stabilization energy for high spin and D4 octahedral complexes. Let me give you the answer is the first one. Then how to calculate this, what is a CFSE or a crystal field stabilization? That is going to be this one. Here, this I will give you very important clue to calculate in a very simple way. Let us see what is this clue. Here, our answer is, this is the D4 electron configuration. It is going to be the -0.6 DQ. See, I want to tell you some important points regarding this one. See, what is meant by low spin complexes and what is meant by high spin complexes. See, whenever a strong ligand is there, see, you know that important point is, you know that this is going to be the d orbital where it is having 5 degenerate orbitals are there. In this, what happens when a ligand approaches? When a ligand approaches to the complex, when ligand approaches the complex. For example, if there are, I will take one example. If there are 3 electrons are there, I will take with these 3 electrons so that you can understand very easily. When ligand approaches, depending on the strength of the ligand, if it is a strong ligand and these electrons are forced to pair, therefore, and here you will get, when a strong ligand is present, you will get like this. That is one electron, that is one pair will be there. Okay, like this. That is depending on the strength of the ligand. Suppose when it is a weak ligand, here this does not force the electron to get paired. That's why you will get a 3 unpaired electron. See, another important is what is low spin complexes and high spin complexes. High spin means more number of unpaired electrons. This is going to be our high spin complexes. High spin complexes will be formed in the presence of weaker ligands, which does not force the electron to pair up. Whenever it is a strong ligand, see, the electrons are get paired because they are forced to pair up the electron. That's why here in this case, what happens, number of lone pair electrons are less. Here number of unpaired electrons are more, here number of unpaired electrons are less. And this what is called as the low spin complexes. What to remember? If it is a strong ligand, this is going to be the low spin complexes. If it is a weak ligand, that is the result in the high spin complexes. Just simply you remember WHS and another one is SLS. That is WHS means weak ligand, high spin complexes, strong ligand, that is low spin complexes. You remember in this way WHS and SLS. In this way you can remember what is low spin complex and what is high spin complex. And another important one is, see, I think you understood what is high spin and low spin. Now, how to write the D configuration for the different, if it is a high spin complex, if it is a low spin complex. And first of all, you have to write the electron configuration for this one. Then after writing the electron configuration, see, suppose if it is a D1 is a, this is does not make any problem up to D1 to D3, because in D1 or D3, the values are same, you see. The values are same, 4 and 4, 8 and 8, and 12 and 12. Here, there is no problem for D1 to D3. Where is the problem? From D4 onwards, again the problem. Okay, up to where here it is again problem, you can see here, D4, D5, D6, and another one is going to be the D7. Again, you remember here there is no problem about here from this configuration. That is D7, D8, D9 and D10. See, here this two does not make any problem. That is, I'll write here this and here this one. No need, there is no difference for high spin and low spin complexes for writing the D term. But whereas what to remember, you have to remember how to write D4, how to write D6, how to write D5, D6 and D7. These are only the 4 terms. If you remember how to write, this is very, very simple. Suppose for the D4, I told you that in the case of the low spin, the electrons are get paid. That is, electrons get paid in low spin complexes because the strong ligand. That is, I told you, SLS. Okay, whenever it is a strong ligand, you simply, I told you now, that is the electrons are get paired. You make it how many pairs are possible that you can make. Okay. Now here this is for the octahedral complexes. Now here for the D4, how many electrons here? That is, you know that this is going to be the T2G and here another is going to be the EG. Okay. See, in T2G, how many electrons are there? 4 means you can write like this. 1, 2, and here it is 3. And in if it is D4, you can write like this. There will be 1 electron here. Whenever it is a strong ligand, this electron is tend to pair up here. Therefore, how many electrons will be there? Here you can write, okay, 4 electrons, no? Okay, no problem, sorry. And here the 4 electrons here, they are in the, our question in the strong field ligand, there is 4 electrons are present in the T2G, but when you come to our question, 3 electrons are there in the T2G and 1 electron will be there in the EG. Therefore, another important is for T2G, you multiply with this 0.4, whereas for EG, with this EG, you have to multiply with 0.6. And here, this is because it is a weak field ligand. In the question itself, it is given high spin. Therefore, T2G3 EG1 0.4 into 3, and it is going to be the 0.6. And here, this is going to plus 0.6. Therefore, here you will get minus 0.6 and plus 12. 4, that is 4 into 3, that is going to be the 1.2, and 1.2 plus 0.6, that is going to minus 0.6, or in terms of dq, it is going to be the minus 6 dq, not plus 6 dq. It is. In this way, you find out, you practice these questions, only these 3. Only for this you practice, then you can have an idea regarding this. Okay, this is a very, very important topic. Most of the examinations, entrance examination, you will get. Now let us see. X is an essential trace element. Its use in industry, particularly electroplating, causes severe water pollution. What is this? 6. Iron, copper, cobalt. And very simple, iron, copper and cobalt, these are not used for electroplating. That is, you know this one. Cobalt is used in what is called, the radioactive cobalt is used in cancer. That is called therapy, that is chemical therapy. The radiotherapy, that is cobalt isotopes are used. Now let us see, the answer is 4. The nickel is used mainly the electroplating. See, I have given this entire discussion about this, but according to our, only the water pollution. See, water containing 250 ppm of nickel from a contaminated drinking fountain had a stomach ache, suffered adverse effect in their blood, even it damages them. If you want, you can read where it is nickel is used and what are the causes pollution that can. Now let us see, another one is the order of the stability of +2 oxidation state of chromium, manganese and iron, cobalt. So let us see, first let me tell you the answer is 1. Manganese complexes are more stable than the iron, more stable than the chromium and cobalt. But in general, they do not follow a particular trend, but very, very important, some generalization also there, and that generalization is like this. The relative stability of +2 oxidation state increases on moving from left to right, that is scandium to zinc. This is because on moving from left to right, it becomes more and more difficult to remove the third electron from the d orbital because the increasing nuclear charge or decreasing size of the ion, just now we discussed. See, okay, I want to tell you one here. See, that's why you can have the answer is this one, because you know that manganese is 25, this is 25, 26, this is 24, this is 25 is higher number than manganese, iron and chromium, cobalt. Here they generally do not follow general trend, but manganese having the d5 electrons, therefore it is not possible to remove the electron in +2 oxidation state. If he has 26 electrons, and a chromium having the only +2 oxidation state 24 electrons, that is 4 electrons in d orbital, whereas the cobalt has +3. But Mn+2 is more stable than the Fe+2, and it is more stable than this chromium. And you remember, chromium +2 and chromium cobalt +2 are not stable. Generally, the chromium exists in the +3 oxidation state. Cobalt also exists in +3 oxidation state. It was not a general trend, these are not followed, but the general trend is with increasing the size of the, going on left to right, the +2 oxidation stability will be increases. Okay. Now come to the another point. Here, which of the following statement is correct? Sometimes you will get here do not correct, not correct. But you find out which is the right statement we have to identify. See, titanium group metals form stable interstitial metal hydrides. Chromium compounds are strong oxidizing agent. Chromium 3. Molybdenum and wolfram differ in their properties. Titanium 4 is less acidic than the titanium 3. Let me tell you the answer is only one. The first only the right answer. Remaining are wrong statements. Let me tell you what are the why it is. First one, interstitial compounds. You know that what are the interstitial compounds? Interstitial compounds is non-stoichiometric compounds mainly formed by lighter elements like hydrogen, halogen, nitrogen, carbon, boron, silicon and sulfur with metals, mainly with certain metals where some interspatial sites are present which are suitable for their atomic size. They will interact with this metal without any forming bond. Okay, here titanium, zirconium, hafnium, the interstitial compounds of these three elements are more stable when compared to the other. That's why this is only the right statement. See, the second statement is wrong. Why? Because chromium plus 3 is not a strong oxidizing agent. This is going to be the strong oxidizing. Chromium plus 6. Suppose if you take the potassium chromate or chromic acid, these are the strong oxidizing agents. And third one is molybdenum. This is M, not M. And here the molybdenum and wolfram differ in their properties, they given the statement, but molybdenum, wolfram and chromium belongs to the same group, that is sixth breed, that's why they show the similar properties. And other one is said to be the titanium 4 is more acidic than the titanium 3. For a given element, if more is oxidation state, more will be acidic property or hardness. This is from the Schaub, Pearson's-Schaub theory and HSCAB theory. Here, the titanium 4 is more harder acid than the titanium. Now here, then again you will get another question on the magnetic property. That's why I told you magnetic property and colored complexes. How to determine this? How to write? How to what is said to be? How to select the correct answer is very important regarding this case. And here, which of the following is having the paramagnetic nature? Which of the following is paramagnetic? Sometimes they ask which is having the higher paramagnetic nature, or among the following which is not a paramagnetic. Like this, you will get a question. Now our question is which is paramagnetic, means remaining or not paramagnetic. Well, how to calculate this one? Let us see. The answer is the third one. This is only the paramagnetic, remaining or diamagnetic. How it is? See, the carbon is having 6 atomic number and oxygen is 8, 14, therefore 14 electrons. It is a even number, therefore all are paired texts. If you take the carbon, it is 6, nitrogen is 7, because it is a negative charge 1, therefore 14, it is a even number. Therefore, whenever it is a even number for a given ion, or when a given ion or a molecule, that will be diamagnetic, because no unpaired electron is possible. And here nitrogen and oxygen, 7 plus 8, 15, it is a odd number, therefore no, all pairing does not possible, therefore one electron remains, that's why it is paramagnetic. Suppose you take this one, nitrogen and oxygen 7 and 8, but it is a positive charge, means loss of electron, -1, that is 14. That's why all are get paired. That's why whenever you get this type of questions, you try to add their atomic number. If it negative charge, add. If it is positive charge, if you get a even number, that is diamagnetic. If you get a that is odd number, that is going to be the paramagnetic. Now, which of the following is insoluble in dilute nitric acid? This question is from our chapter, that is going to qualitative analysis, but it is related to some what is called mainly transition metal. That's why I took here. See, this is the question. Answer is only one. Here, it does not dissolve in what is called dilute nitric acid. Let us see. Actually, mercuric sulfide is the only. It is only soluble in aqua-regia. It does not soluble in any other solvents. What is aqua-regia? Aqua-regia is a mixture of 1:3 ratio of concentrated nitric acid and concentrated hydrochloric acid. And it is soluble only in aqua-regia. It never soluble, or it does not soluble in any other solvents. And see, this is the group 2 cations, lead, Cu+2, bismuth+2, Hg+2, and Cd+2. These are the 5 cations are there in group 2 in salt analysis. They are identified by treating with the hydrogen sulfide in presence of HCl. Then if it is Pb is there, you'll get the black PPT, copper also black PPT, but the bismuth gives the brown PPT. Whereas mercuric sulfide, it may be red or black, but wherever cadmium sulfate, it is yellow color that you get. Now see, these are the different reaction when dissolves in the nitric acid, and the Pb, bismuth and copper, they form the sulfides, and their colors here mentioned. And when they are dissolved in nitric acid, they liberate nitrogen dioxide. That's why they are soluble. Whereas mercuric sulfide is not soluble and soluble only in aquaresia. Now let us see, other one is said to be the, okay, I want to tell you this one. See, the color of the HgNH2Cl is. This is also from our qualitative analysis. Red color, yellow color, black and white. Our answer is this 4. It is going to be what is called as white in color. It is not any other color, it is white in color. Okay, I want to tell you one more important regarding this reaction. This is an example for disproportionation reaction. That means self-oxidation and reduction. That is, in a reaction, when a single element undergo oxidation as well as reduction, such reactions are called disproportionation reaction. In Hg2Cl2, you know, chlorine is the -1. Therefore, on calculating the mercury, you will get the +1 charge. See, in the HgNH2Cl, amide has -1 and then chloride has also -1. Therefore, to satisfy these two, here the mercury is having +2. Okay, you know, I think you know that how to calculate oxidation state. Here the mercury is in uncombined state, therefore it is having 0 oxidation state. Now see, the mercury from +1 to +2, this is going to be the oxidation. And the mercury from +1 to 0, decreasing oxidation, this is going to be the reduction. This type of reactions are called disproportionation reactions. Okay. And I hope you understood clearly this one. If you are like this this video, you please subscribe and share among the students, which is very useful for them. Thank you for watching this video, and we will meet with in another session.